Okay, so welcome to the deep dive. Today we're jumping straight into something really crucial: secure communication between smart contracts on the Ton blockchain.
Yeah, with decentralized apps growing so fast, figuring out trust without a middleman is, well, it's everything.
And the old ways of checking who's who, traditional authentication, sometimes they just don't quite cut it in this new world.
Exactly. We're moving beyond just asking who sent a message. Today, we're going to explore this really fascinating concept called DNA checks.
DNA checks. Sounds intriguing.
It is. It basically lets a smart contract look at the code of another contract to verify its identity.
hmm
Think of it like checking its fundamental blueprint.
So not just the address, but the actual programming underneath.
Precisely. It's about verifying the kind of contract you're dealing with. Is its logic what you expect? It's a way more powerful check in many cases.
Okay, that makes sense. So our mission for this deep dive is really to get under the hood of these DNA checks. How do they work?
Yep. And why they're so important, especially when you have like a main contract managing lots of smaller ones, this parent-child setup.
Right, which ties into how Ton scales, doesn't it?
Yeah.
Distributing the work.
Absolutely. We'll explore why this is vital for security and making Ton handle lots of traffic. DNA checks are kind of a foundational piece for building complex, trustworthy apps on Ton.
And even if authentication sounds a bit dry or technical, stick with us because this really gets into the nitty-gritty of how trust actually works in a decentralized world.
Totally. It's actually quite elegant when you see it in action. Whether you're new to blockchain or you've been around the block, there's some cool insights here.
All right, let's do it. To really grasp why we even need DNA checks, maybe we should quickly recap the usual ways contracts authenticate on Ton first. We touched on some basics before.
Good idea. So there are essentially three main ways. The first one is probably familiar to most people: signature-based authentication.
That's for messages coming from outside the blockchain, right? Like from my wallet.
Exactly. When you send a transaction from your wallet app, it gets digitally signed with your private key.
Uh-huh.
Then your wallet contract on Ton, the smart contract representing your wallet, checks that signature using your public key. Only then does it pass the message along.
So the wallet contract is like the gatekeeper for the external world talking to Ton.
Perfect analogy. It's that critical security boundary. Your signature is like your passport stamp.
Okay, got it. Signature checks for external stuff. What about communication inside Ton between smart contracts?
Well, for internal messages, things are simpler and way more efficient. That's the second method: message sender authentication.
Simpler how?
The Ton protocol itself basically guarantees that if contract A sends a message to contract B knows the message genuinely came from contract A's address.
Oh, so it's built in, like MSG.sender in Ethereum, sort of.
Exactly like MST
Fine.
Sender. It's baked right into the core rules of the blockchain.
Yeah.
No need for complex signature checks between contracts.
Which must save a lot of time and processing power, I imagine.
Huge savings. It's
Yeah.
much faster, much cheaper in terms of fees. Very efficient for internal chatter.
Okay, so built-in address verification for internal messages. Sounds pretty solid. But I sense a but coming. Where's the catch? Or rather, where does the need for something more like DNA checks arise?
Well, the but comes from Ton's fundamental design. It's built around asynchronous messaging. Contracts send messages back and forth, but they don't, call each other directly and wait for an immediate response in the same transaction.
Right, they fire off messages and they get processed later, potentially on different parts of the network, different shards.
Precisely. And that async nature is key for scalability, for processing lots of things in parallel across those shards. Think of it like sending letters instead of making phone calls.
Okay, letters instead of calls. Makes sense for handling volume.
But because there's no shared immediate phone call context, a contract receiving a message, even though it knows the sender's address, might need more assurance in certain situations.
What kind of situation?
Imagine a contract that's designed to interact with, say, hundreds or thousands of other contracts, maybe dynamically created ones.
Ah, okay. You can't just keep a list of every single trusted address then. That list could get huge and slow everything down.
Exactly. It becomes impractical, a bottleneck. So the big question becomes, how can a contract trust the origin or the type of sender when there's no synchronous link? And maintaining huge whitelists isn't feasible.
And that is where DNA checks step in.
That's the cue. DNA checks provide that extra layer of verification.
So let's define it clearly again in this context. What is the DNA check doing?
So instead of just relying on, yep, this message came from address X, the receiving contract performs a check on the sender's fundamental nature. It validates the type of code, the structure of the sender contract.
It's like saying, okay, I know who sent this, but are they the kind of contract I'm supposed to be talking to for this specific action?
You nailed it. It ensures only contracts with a specific verified logic, a specific DNA can trigger certain functions. It shifts from just who to what.
That sounds powerful. When is this kind of check most useful? You mentioned contracts interacting with many others.
Right. That's one key case. Another massive one is in those parent-child architectures we mentioned.
Okay, explain that more. The parent-child thing.
Imagine a central parent contract, maybe like a factory, that creates and manages lots of smaller child contracts. Each child might handle a specific user's data or a specific task.
And this helps ton scale, you said?
Immensely. Instead of one giant contract holding everything and getting bogged down, you distribute the data and the workload across potentially thousands of child contracts.
Which can run in parallel on different shards.
Exactly. Parallel processing. Think of the Jetton Standard Tons version of fungible tokens, like ERC20s.
Okay, yeah.
With Jettons, there isn't one huge contract listing everyone's balance.
Yeah.
Instead, each user who holds that Jetton gets their own tiny, dedicated Jetton wallet smart contract.
So I have my own little wallet contract just for my sample Jettons. You have yours. Everyone has theirs.
Correct. And these thousands of individual wallet contracts could be spread all across Tons network on different shards, handling transfers efficiently.
Wow, okay. So in that Jetton example, how would DNA checks be used?
Well, think about it. The main Jetton contract, the master, or even other Jetton wallets need to be sure they're interacting with genuine Jetton wallets of the same type, not some imposter contract.
Right. You need to verify that a child contract claiming to be a wallet for this specific Jetton actually is one deployed correctly and not some fake.
Precisely. Especially if those child wallets perform actions that affect the overall system, like transfers. You need to trust they were created by the right parent and follow the right rules. The DNA check confirms that authenticity based on the code structure.
Makes sense. And you mentioned another use case, something about calculating addresses.
Yeah, sometimes a contract needs to figure out the address of another contract on the fly, rather than having it stored permanently. DNA checks make this way more secure, because you can calculate the expected address and verify that the contract at that address has the correct code DNA.
Okay, so it's about trusting dynamically generated or numerous counterparties. Very cool. Let's get into the mechanics then. How does a contract actually do this check? How does it see the DNA? Keep it understandable, though.
Okay. No deep dives into assembly code, I promise. The core principle is actually tied to how ton addresses are created in the first place.
Oh, they aren't just random numbers.
Not at all. A ton smart contract address is a cryptographic hash. Think of it like a unique digital fingerprint. But it's a hash of two specific things combined. The contract's actual code.
The blueprint.
Right, the blueprint.
Yeah.
And its initial data, or initial state, what we call the state in it.
State it, like
Yeah.
its starting settings when it's first deployed.
Exactly. The code plus those initial settings are crunched together using a cryptographic hash function, and boom, out pops the unique address for that contract.
Okay, code plus initial state and address. But what happens when the contract runs and its internal data changes? Does the address change too?
Ah, that's the crucial part. No, it doesn't. The address is based on the initial state and the immutable code. Even if the contract's internal variables change later, like a balance increasing the address, that fingerprint calculated at birth stays the same.
Whoa, so the address is forever tied to the original code and setup.
Correct. It acts as a permanent cryptographic commitment to that specific code and initial configuration. Any tiny change to the code or the intended initial state would result in a completely different address.
I see. So that's how you do a DNA check. A receiving contract can look at the sender's address and know cryptographically that this address must correspond to a specific piece of code and initial setup.
You got it. It's not just who sent it, but the address itself implicitly tells you what kind of contract it is, because only that specific kind of code and initial data could produce that exact address.
The code becomes its own verifiable ID baked into the address. That's actually really elegant. Okay, let's ground this. The Jetton example again. Alice sending sample Jettons to Bob. Walk us through it with DNA checks in mind.
Perfect. So remember, we have the Jetton master contract for sample Jetton, controls total supply, minting, and individual Jetton wallet contracts for users like Alice and Bob.
Got it. Master contract and personal wallet contracts for each user holding that specific Jetton.
Right. So Alice wants to send Jettons to Bob. First, her wallet app needs to figure out the address of Bob's Jetton wallet for sample Jetton.
And it doesn't just ask Bob.
Nope, it calculates it deterministically. It needs a few ingredients for this calculation.
What ingredients?
It needs the standard public code for the Jetton wallet contract. Everyone uses the same code for a given Jetton type. It needs Bob's own blockchain address, the owner. And crucially, it needs a unique identifier for the specific token, the address of the Jetton master contract for sample Jetton.
Okay, standard wallet code, Bob's address, sample Jetton master address.
Yep. Conceptually, Alice's wallet runs a function like calculate user Jetton wallet state init. This bundles Bob's address as owner, sets an initial balance of 0, very important, and includes the sample Jetton master address.
0 initial balance, why 0?
To prevent anyone from just deploying a wallet contract for themselves that magically starts with 1 million tokens. Only the master contract can actually add tokens later.
Ah, good security point. Okay, so it bundles this initial state. Then what?
Then it takes this statement and the standard Jetton wallet code, hashes them together using another function like calculate user Jetton wallet address, and gets Bob's unique wallet address for sample Jetton.
Okay, so Alice's side now knows the exact address for Bob's sample Jetton wallet. She sends the transfer message there.
Correct. The message goes to that calculated address saying transfer X tokens from Alice's wallet. Now, Bob's Jetton wallet contract receives this message.
And now Bob's wallet needs to be sure it came from Alice's actual sample Jetton wallet, right? Here comes the DNA check.
Exactly. Bob's wallet now performs essentially the same calculation Alice's wallet did, but in reverse, using Alice's info.
How does it know Alice's info?
Alice's address is included as the sender in the message. So Bob's wallet takes Alice's address, the standard Jetton wallet code, its own code, and the sample Jetton master address, which it knows as it's part of its own state.
Okay.
It calculates what Alice's Jetton wallet address should be for sample Jetton using these ingredients.
And then?
Then it compares the address that just calculated for Alice with the actual sender address attached to the message.
Where?
Ample gender, a simple check quality, calculated Alice wallet address, actual sender address.
And if they match?
If they match, it's cryptographic proof. It proves that the contract sending the message, the MFIG sender, has the exact same code DNA, the standard Jetton wallet code, and is linked to the same Jetton master, sample Jetton, and is owned by Alice. It must be Alice's genuine sample Jetton wallet.
Wow. So the check confirms the sender is the right type of contract, a wallet, associated with the right token, sample Jetton, and owned by the right person, Alice. That's incredibly thorough just from checking the address against a calculation.
It is. It ensures the whole interaction stays within the legitimate ecosystem of that specific token.
Okay, but you mentioned a potential issue earlier, a caveat. What if, say, sample Jetton and, I don't know, example coin both decided to use the exact same open source code for their wallet contracts?
That's the crucial edge case. If the address calculation only used the owner's address and the wallet code.
Then my address for sample Jetton wallet and my address for example coin wallet would be identical.
Exactly. Big problem. You'd have collisions, confusion, security risks.
So how is that avoided? It seems vital.
It's avoided by that third ingredient we mentioned in the calculation, including a unique identifier for the token itself within the initial state init.
The Jetton master address.
Precisely. The standard practice, defined in TEP 74, the Jetton standard, is to bake the unique address of the Jetton master contract for that specific token into the state init used for calculating every user's wallet address for that token.
So the calculation is really wallet address hash, wallet code plus initial state init, owner address plus master address plus 0 balance.
You've got it. That Jetton master address acts as a namespace, a unique salt. Since sample Jetton's master address is different from example coin's master address, even if they use the same wallet code.
My wallet address for sample Jetton will be different from my wallet address for example coin. Oof.
Exactly.
Expected.
It adds that vital layer of uniqueness, ensuring addresses are specific to both the user and the particular token.
That really ties it all together. So when you're interacting with, say, a Jetton wallet on Ton, you're not just trusting an address someone gave you. The system itself, through these DNA checks embedded in the address calculation and verification, is cryptographically ensuring it's a genuine wallet for the correct token.
That's the beauty of it. The code's identity and its link to the specific token standard are verifiable just by knowing the address and the rules. It builds trust right into the system's fabric.
It really is an aha moment when you realize the code itself becomes this verifiable identity marker. So wrapping this deep dive up, DNA checks on Ton are, well, they're clearly a very smart authentication mechanism.
Definitely. Way beyond just basic address checking. They use that deep cryptographic link between code initial state, and the resulting address.
And it seems absolutely essential for building secure apps that can actually scale, especially using patterns like the parent-child model we saw with Jettons.
Couldn't have said it better.
Yeah.
And for you listening, hopefully, understanding this gives you a real appreciation for the kind of innovative security thinking going into platforms like Ton.
Yeah, it shows how you can build reliable trust systems without needing a central bank or validator saying, yep, that contract is legit. The math and the protocol do the work.
It's decentralization in action, really. Pretty powerful stuff.
Absolutely. Which, thinking about it, leads to a really interesting final thought for everyone to chew on. DNA checks rely heavily on the code being fixed. Immutable, right? That's what makes the address a stable fingerprint.
That's the foundation, yes. The immutability of the code hashed into the address.
So, what happens if you need to upgrade a smart contract? If you change the code, you change the DNA. Doesn't that potentially break all these DNA checks and trust relationships built on the old code's address?
Now you're opening a fascinating can of worms. Contract upgradability in a system that relies on code immutability for identity. That's a whole other challenge.
Indeed. A topic perhaps for another deep dive. How do you handle upgrades when the code is the identity? Something to ponder. Thanks for exploring DNA checks with us today.
My pleasure. Till next time.